Let's talk about the convolution, but we will talk about multi-dimensional convolution. So simple convolutions are easy to understand. They're actually very similar to matrix multiplication. So if you think about the matrix multiplication, right? So when you're multiplying, for instance, matrix A by matrix B, you want the number of rows in right matrix to match the number of columns in the left matrix, left argument. So when you are doing the convolution, then one-dimensional convolution, then you almost want the same thing, except B doesn't need to match the number of columns A. It only needs to be lesser than or equal, and then you will produce the convolution result, right? So I'm not going to talk about one-dimensional convolution, but I'll talk about three-dimensional convolution because it's a little bit more difficult to understand sometimes compared to one-dimensional or two-dimensional convolution. So what is the idea of a three-dimensional convolution? So let's look at matrix A. So in this case, matrix A is it has two dimensions, right? It is two by 4 by 3 matrix, right? And my B matrix is 2 by 2 by 2. This is my kernel matrix, right? So you have this first dimension has 2 elements, right? The second dimension has 4, and the third dimension has 3 columns. And then this one is 2 by 2 by 2. So how do we do convolution? So think about this, like the very simple convolution I'm running here. Let's look at maybe second row, second column element, right? What is going on? So I am basically multiplying this matrix you are seeing here by the matrix by the first element of B, and then this part by the second element of B. Why? Well, because you see, basically in convolution, when you don't have strides and other, like the most simplest three-dimensional convolution, you're just running across 3 dimensions. I have 3 dimensions in my matrix A and 3 dimensions in matrix B. So I'm basically running the convolution almost like at the same time across all the dimensions, right? And so I am getting the matrix C with only 3 by 2. Why? Because see, the number of layers in matrix B, first dimension matches the first dimension of A, so there's going to be only one element, and because of that I can basically think of this matrix as just 3 by 2. So it's a simple convolution, you multiply and then add, right? Now so maybe let's look at the first element, maybe first column and second row and first column. You see? So it's almost the same, right? And then if we do second element, second column, we're moving to the right. So simple convolution operator. How do we implement it in Python? So I reproduced basically these tables, right? So I recreated the table A and table B. Came here, and then I'm using conv3d function for three-dimensional convolution from functional interface of my torch. I didn't do it in NumPy, right? So I'm doing it only in torch because that's where you probably would be using it anyways. So it's as easy as just saying convolution 3D, and then you just basically say matrix R and matrix F. But I'm doing something strange here, right? So I'm adding dimensions here. Look, to both R and F, which are these matrices, I had to add 2 more dimensions, so I made them both 5-dimensional. So they are 3-dimensional initially, but I made them both 5-dimensional by adding 2 dimensions in front of them. Why am I doing it? I'm doing it because this conv3d is written for convolutional neural networks. And for neural networks, it happens so they need 2 more parameters. They have because the way the convolutions work, they work on multiple input channels, and they work on multiple output channels, and so on. So I'm showing you the simplest convolution here. Conv3d can get quite complicated in PyTorch framework, right? So we know from the formula in the class we studied it that if my first dimension is 4, for instance, in this case, or rather I'm doing convolution on 4, 3, 3, 2, 2, 2, right? So think of this, my convolution is on later two dimensions, and because of that my 4 plus 4 and 2 to know how many rows I will have in my output, I need to get 4, right, and subtract 2, second dimension, number of rows here. Because you see, you will do one, right, convolution, another one, and third one. So that's your convolution. And that's why you have only 3 rows in the output. So my input is 4 rows, but my output is only 3, right? Again, why? Because my filter has, or my kernel has 2 rows, and it's going to be a convolution like this, convolution third, and convolution third. Only 3 steps I can make. If my stride is 1, if my stride is bigger, then it's even lesser than that, right? So I got that 3 outputs. So sometimes I want my outputs, my output size, to be the same as my input size, and my input size is 4 rows, right? And here I have only 3. Sometimes I want to have all 4. So what do I do? So in this case, I can convolve with padding. So when I'm running the convolution, I can say do the padding. How the padding works? The padding takes your original matrix and pads it with maybe zeros or something. So in this case, I'm padding it with zeros. So if I pad it with zeros, I show them in these grays. It's kind of like implicit. It's like underneath. You don't have to see it. So I pad them with zeros like this. I pad them with zeros like that. And not only that, I padded this whole entire new layer with 0, 0, zeros. Why? Because then you see, when I start running my convolution, let's say across first my second dimension, right? It's like first, second, and third dimension. So let's say I'm doing it across second dimension. Okay, one convolution, second step, third step, fourth step, because I padded, right? And that's how in my output I have 1, 2, 3, 4 rows. Let's look at the first dimension though. My first dimension is layers, right? And now because I padded with additional layer my matrix A, now when I'm convolving, first I'll run this, right? Okay, was my first convolution. And my second convolution is second layer and third layer. And that's how in my output I have 2 layers, right? Because I had 2 layers in my input. Now let's look at the columns. In my columns, my last dimension in my output, I had 3 columns. So I padded with 1 more, and then when I'm convolving, this is what's going on. 1, 2, and then I'm getting into padding 3. So that's how I have 3 columns here. So you can look at my formulas here, right? Examine the formulas. So that way I have the same number of exactly the same dimensions of my output, right? 2 by 4 by 3 as my inputs, all right? 2, then by 4, and by 3. So to accomplish that, to achieve that in Python, in Torch, I do the same exact command conv3d. Again add those fake dimensions, empty dimensions. But I'm saying padding is same. Same means that I tell my padding I want the same dimension of my output as my inputs. So that's what same means, and it will do the padding at the end. So I was able to reproduce these outputs in Torch exactly how they appear on Excel, right? So no padding output and padding output on the right hand side. So this was on the convolution. So these are the basic operators with PyTorch and NumPy. So let's think about it. When you would use NumPy and when you would use PyTorch. So the major difference to me between PyTorch and NumPy, at least at this moment, is that PyTorch framework is optimized for GPUs, graphical processing units, and through this interface called CUDA, which was created by NVIDIA Corporation. So NVIDIA produces probably the most popular GPU processors, this hardware which is very fast for graphical processing, and it happens to be fast for neural networks, convolutional neural networks too. So that's one thing. The other thing, through CUDA, you can also, that interface called CUDA, CUDA, you can actually access non-NVIDIA hardware like Google's Tensor processing units, things like that. So basically, Torch is similar, PyTorch is similar to another framework called TensorFlow, which was developed by Google initially. So these are, created to sort of optimize, make it easier, faster to run the neural networks on very fast hardware. NumPy is very good at operating numbers, arrays, numerical arrays, numerical computations, linear algebra, stuff like that. It has access to this very powerful linear algebra packages, which has been written like long ago in Fortran, like 50 years ago. So, but they're very fast and optimized, things like that. So they have different applications, I would say. So if you're doing neural nets, the key, the main thing which you want is you want them run fast. These like neural net calculations, like convolutions and so on fastest hardware like GPUs, and you will tend to use Torch. And for like general numerical calculations, I think NumPy is enough. So if you're not doing neural nets, then maybe you wouldn't be using Torch. Although again, if you have access to very fast, specific, specialized hardware, then maybe Torch will still be the choice. So you can use both. As you can see, you can convert from one to another. I tend to use NumPy most of the time for simple calculations. I find it easier to deal with, but on the neural nets, of course, you'll have to use Torch. And that was it. Thank you.